sort of the intro method you mentioned on the side. If you want to talk about dimensional reduction, right? It's pretty much the first slide after the introduction. It's principal component analysis. And in metrology, there are not just one book written about it, but series of books written about different ways of dimension reduce and make them more interpretable in different rotations. And it's quite a zoo of ideas and methods and concepts, and I will only be able to touch on the very surface of it today. And what I will try to do as well, maybe for the meteorologists in the room, is if you have ever been confused by principal components, I can assure you, and by EOFs, I've been confused too, because the notation in different books is always different. So I will try to keep it as consistent as possible over the slides. And it might differ from some of the literature recommendations that I put here. So just be aware that U is not always U, V is not always V. Sometimes there's a lambda and an S and a lambda that is interchanged. So notation matters, right? So what I will try to focus on is ideas that you can use, and just try to take them as a guideline whenever you read those texts and think about those core ideas and try to map whatever is written onto those, because it can be quite confusing. And the next problem that comes into play is that often it's applied in fields where people want to use it in a way and then again use a different notation and talk about the same things with different terms. And metrology is just a very good example for this, because principal components, as you certainly have heard before, are essentially a way of transforming an orthogonal transformation of your data into a potentially lower dimensional feature space. And what you get is sample representations that are mutually uncorrelated in time series, which we usually have in climate and science and meteorology. The time series would be uncorrelated at lag 0, right? So, but they could be correlated actually, and that's another thing people often overlook, at lags, right? So suddenly they could become correlated again. And often in climate science meteorology, we're interested in lags. And if you do the vanilla eigen decomposition, you would also get principal components ordered by variance. So how much of the variance to the total signal in your data represent. And often in papers, like here in Nature Biotechnology, you would see something like this. 2D, you can visualize a variance in the data, Gator 3 against XBP1, I don't know what that is exactly. Correlated, and you see there's a lot of variance, but correlated variance in this dimension. So the first principal component, as they would call it here, goes in this dimension, and then the next one has to be orthogonal to it. And this is this orthogonal transformation that we talk about. I know the time is overlaying this here, but I think you can imagine that this is the first component and this is the orthogonal second component that lays through this data. But clearly, this is a very simple two-dimensional way of looking at this, and it's very flippant in the way of using the definition of PC in this term. We try to be somewhat more consistent here. So fundamentally, what you're doing is you have a data set, let's say with n samples. Usually I will talk about time series here, so later on I will also use the index t as a result if we talk about time. And you have p dimensions, let's say in the first place, so you're an RP, p features that you want to represent. And you want to have, in the first place, before you do a dimensional reduction, linear approximations to that data, and that can be of rank p or smaller, right? If you have feature sets, for example, represent exactly the same information. And usually these are used for dimensional reduction by, for example, choosing a number of components that is smaller than the initial number of features that you had, or for data compression, and so on, to retain a certain amount of variance, which is proportional to the eigenvalues, as you will see later on, of the components. Now, I talked about different fields referring to these in different ways, and metrology is maybe the best way of putting this, because in metrology, most of the papers refer to it as empirical orthogonal functions, but it's exactly the same. So don't get confused by this. So this is often referred to as EOFs in metrology. And why this is the case, I will come back to on the next few slides. And now you can do the eigendecomposition in different ways, but the most common one is probably singular value decomposition. So I will also try to clarify, if you haven't seen this before, of how SVD links to the original eigenvalue eigenvector decomposition. Now, the atmospheric science view on PCA, so atmospheric science for me encapsulates meteorology and climate science, is that, and I showed this timeline in my first lecture for how machine learning came into climate science or environmental science. Probably what boosted principal components in meteorology was a paper by Lawrence. He was, I think, also connected to the butterfly effect, who introduced also the EOF, empirical orthogonal function terminology. And this was in 1956, but actually, if you look back into history, first applications were already done in 1947. So this concept has been around for really a long time, and this is probably why it's so well evolved in meteorology in particular. Now, when we talk about PCA, you will get eigenvectors, which become very important, and they basically define a new coordinate system. And this is also where the name empirical orthogonal functions in meteorology comes from, because the logic here is that you define orthogonal axes, and these orthogonal axes will be different if you apply PCA to different data sets, right? So the coordinate system that you learn in that sense is defined empirically. And this is why the orthogonal axes and empirically defined, you have empirical orthogonal functions. And the original aim in meteorology is clearly that you often have this gridded data, which can be quite hard to interpret, high-dimensional, multiple time steps. So you have dimensionality, both in terms of the number of samples, a lot of samples, and then in space. And you would like to see correlations across those patterns. So the original idea could we decompose the complex high-dimensional data structure, especially in space, into a series of optimal basis functions in its form, this transformation and expansion functions of time, here written in a sum notation. If you don't like the sum notation, it's just given for you to orientation. You can fully focus on the matrix formulations that I will use later on. But this was the original idea. And clearly this approach can only be useful if we could, for example, approximate the system due to substantial correlations across those features, let's say different grid points, again, so that you can dimension reduce or represent the variance in the system by a much smaller number of retained components or principal components, M, that could be much lower than the rank of the original data matrix. And the good thing, and this is why it's so widespread in atmospheric science, is that this is often the case, because let's say meteorological variability over Switzerland is quite highly correlated with meteorological variability over eastern France and southern Germany, right? So there is common information in here. Is there any question, or is it just too much repetition? So let me go more quickly if you like. So overall, the aim is an efficient representation. So what is the connection between principal component analysis and singular value decomposition? If you do this, originally you start off with the sample covariance matrix, or if it's standard scaled, so not just zero-centered, it's often also referred to as the sample correlation matrix, which I denote here as C. And this is then one way of doing the eigendecomposition would be to diagonalize this matrix into the eigenvectors, denoted as V here, so often they are also referred to under different letters, and this diagonal matrix L in the center, which contains the eigenvalues, right? And I'm pretty sure you have seen this in linear algebra before of this kind, so you know what eigenvectors are and what eigenvalues are in this case. Now, following singular value decomposition and how it's typically implemented, and you will do this as well in exercise 7 yourself by hand, because I think, especially for the rotations, that's quite useful, that follow later on. You basically start, you could also SVD the covariance matrix, leads to basically the same results. But what you do is you decompose the original sample covariance matrix into a unitary matrix U, a diagonal matrix S again, which you will see is slightly different to the diagonal matrix L here, but connected, and an orthogonal matrix V, which we will see is later on exactly the same eigenvector matrix, depending on your definition as for the eigendecomposition in the first place. Now, very important in a practical context is that in many applications, you will, for example, have more grid points and therefore more features P than you will have samples, right? So in that case, the dimensions of your matrices will be defined by whatever is smaller, right? So either the number of samples or the number of features you put in the first place. And this is often an option you will see in PCA decompositions or singular value decompositions if you want to have full matrices or sparse representations, because depending on this, it might cut off your dimensions or use the full dimensionality, but then you have superfluous information, and especially if this is large, you carry around matrix structures that don't tell you anything. So what is the exact connection here? So we have the covariance matrix being decomposed into VLV, and we have the original data matrix, sample matrix, decomposed into USVT, so USV transposed. So if you write C in terms of X, you can reformulate this quite neatly into just that you can see immediately that the matrix V basically represents the eigenvectors as they are defined, and that L is equal to S squared over n minus 1. From this you can derive that the singular values in the matrix S are basically connected, are basically the square of the eigenvalues divided by the sample minus 1. The sample number minus 1 is clearly just down to the moments. So if you have already taken the zero mean off, that's just for correctness, but practically n and n minus 1 will usually be very similar. And in many implementations it's basically ignored, I believe. Yeah, a few more terms. So now it becomes important. So this is just about the equivalence of why we can use SVD, and you will use this to do the PCA decomposition. So using SVD, we can find the eigenvectors, and you find the singular value diagonal matrix, which you can then use to, for example, estimate the eigenvalues. You will do this in the exercise sheet from the eigenvalues. You should be able to quite easily research this online. If you don't know it, you can reconstruct the represented variance by each of these eigenvectors inside the eigenvector matrix here. Now, what you actually look at in typical applications are the PCs, though, so the principal components. And these are these uncorrelated linear combinations of the features in the first place, right? So how do you obtain those? This you obtain by multiplying the original data matrix times the eigenvector matrix, and this will also just be equal to the unitary matrix U times S. And you can try this at home quite literally. It will give you the same results on assignment 7. Now, in the literature, you will find a lot of loose formulations talking about scores and loadings. So I gave some definitions here. Loadings are usually strictly referred to as the eigenvectors scaled by basically the singular values here. So it gives you some variance representation, scaled representation of the eigenvectors. Now, when I look at these sort of definitions, I think the matrix definitions are quite straightforward, but and you might have your own intuitions about what the eigenvectors represent, but I think in metrology it's quite nice to see later on that they are not always interpretable, and why it's useful therefore to have alternative formulations. So just in case, I think you can always use these sorts of equations to construct the principal component time series, when we talk about time series later on, to reconstruct the transformation of the data into the eigenvector space. But because these are all linear combinations, you can also write this as a sum. So the principal component time series at each time step t, it's basically a linearly scaled sum of the input features. So your feature representations, this could be sea level pressure at a given grid point or so, times the value for the eigenvector for that grid point. So how that exactly looks like, you will see a few examples later on. But it's just a transformation in that sense. And again, typically in this field here, you will look at time series, which means that I changed the sample index here to t. Now, when you look into the metrological literature or the Wilks books, you will also see Wilks book, you will see that the PCs, so the principal components in the classic way, are often also referred to as EOF expansion coefficients, whereas the eigenvectors and their spatial distribution is typically referred to as the EOFs themselves. So the empirical orthogonal functions are the eigenvectors, but the principal components, which are often sort of in casual speak, used to say, let's do a principal component analysis, and these are the principal components. The principal components are these linear weighted representations of the original data, which in our case will usually be time series that represent also the variance in the data. Okay, and again, this is just a different way of writing this. So if you then want to reconstruct X in the first place, you could also see this as a singular value, which is proportional to the eigenvalues, right? Scaled version of the unitary matrix times the eigenvector for each individual case, up to rank R of the original eigenvalue decomposition. But what we actually want to do in most cases is not to keep the entire rank of that matrix, but to select a reduced dimensionality, for example, representing a certain part of the linearly explained variance, or the first 100 principal components, so that we dimension reduce the data effectively, let's say from the original rank R to some smaller dimensionality K. And that clearly means that we have to throw information away as well. So you can write this quite easily. I wrote specifically what you do for each individual matrix here. You keep different parts of it, but basically what you do is to keep the first K eigenvectors, the first K singular values, let's say ordered by eigenvalue representing the order of variance that each principal component represents. And this clearly means that you have some sort of compression. As already mentioned, so the principal components, which are just equal to the transformed initial data, right, through the eigenvector matrix, are usually referred to as the time series when you have time series applications, which just show the evolution of the system over time as seen through that first eigenvector, whereas the spatial patterns of the eigenvectors are referred to as the EOFs. And if you have spatial information, and usually you have longitude-latitude coordinates, which you flattened into a single vector to have a vector representation for the eigenvector. So if you do this, you might have to reshape this onto a longitude-latitude grid, right? So you always have to be aware of what your features actually represent. But the very important thing is, every time you talk about PCA, is that the PCs will be uncorrelated among each other, which for the time series specifically means at the same time step, same months, same day, the time series will be uncorrelated, which is quite a thing. But they don't necessarily have to be uncorrelated if you go further into the past. So if you say use leg 1 of one principal component and compare this to the current time step for another principal component, there might be correlations again. And the EOFs, which are the spatial patterns through which the data is transformed or weighted, are the empirical orthogonal functions or the eigenvectors. So because I feel that some of you might find this still confusing, I think once you have implemented it, it makes a lot of sense. Then let's look at one specific example of December. So winter, northern hemisphere, winter time, summertime for the southern hemisphere, daily sea level pressure anomalies. So here's just a snapshot from a few weeks ago, before Christmas. You see that the color bar is slightly saturated in certain parts of the Pacific here, but basically you have anomalies, levels of variability. You can see that there are high pressure systems in a sort of wave-like fashion over the southern hemisphere here. So you see typically interchange of low pressure and high pressure systems in the mid latitudes and so on. And I do this, very important, and I maybe should have shown this earlier. When I talk, I try to emphasize this point a couple of times already, but when I show these smooth plots of sea level pressure anomalies, what really we have is high dimensional arrays of features where each grid point, this is gridded information, right? Each grid point is a feature, right? And basically what you're trying to do is to find correlated structure across those grid points at a given time step, right? So let's say this grid point I mentioned Switzerland earlier on, is that correlated with a grid point just next to it? And very likely it's going to be, because we have larger scale structure, especially on a daily basis in the system. So what meteorologists always try to do is, looking at this complex weather map, can we study certain modes of variability that sort of seem to run in sync and drive global variability in weather and climate over time, for example. So basically you look at a long time series of weather anomalies running through, and then you would try and find if, let's say, neighboring grid points, for example, show common variability. And as you will see, principal components can't really, don't look at it from a spatial point of view. So what they do is first find commonalities that are globally spread out, and that makes it difficult to interpret. But you look at time series of this, where each time step is a sample and each grid point is a feature. Now the easy way to do this is to use scikit-learn or there are many different implementations, right? But scikit-learn is clearly something that is the baseline go-to method for you in data science, because it contains so much, and there it's very simple. You just take PCA and apply it to a matrix of the dimensions that we talked about, so number of samples, number of features. So you have flattened your grid locations for this. And then you can specify, let's say, the number of components or value between 0 and 1 to keep a certain fraction of the linear variance. What you get out of this is a PCA components, and this is where I find it interesting to interpret again. The components will be the eigenvectors, or the right singular vectors of this matrix. So again, in terms of notations and the messiness, the components in this case will be the eigenvectors, and they will be sorted by explained variance, but they don't give you the PC time series. They don't give you the principal components. They give you the eigenvectors. Here we go. I've said it, right? So don't do it wrong. Let's look at how this would apply. So if we apply this to 75 years of daily data and just show the first eight components, which in this case would be the eigenvectors, and I used scikit-learn for this, you would see patterns like this. So sort of a large negative loading for the first component, which is index 0 here, but you can see that the components are pretty much spread out over the entire globe, right? So especially component 8 here pretty much has a loading or a weight everywhere. Loading would not be quite correct, because then you would have to scale it by the singular values as well, or the eigenvector. So what I want to bring across here, with these first 8 components, you can already explain, you can calculate this from the eigenvalues, 36.5% of the linearly explained variance in the data, to the point that this is represented in the 75 years of data in the system. And what we plot here is the right singular values are eigenvectors. So this would also be referred to as empirical orthogonal functions in metrology. So these are not the time series. So originally I had a question for you, but I'm running out of time.